The universe is secretly stitched together by invisible bridges. These cosmic structures, known as wormholes, link black holes across impossible distances through the fabric of space and time. Stay with us, and by the end, you will understand how these bridges could redefine the future of space travel and our entire cosmic reality. We will uncover why the center of a black hole might not be a dead end, and how a network of these tunnels could connect the entire cosmos. What does it truly mean for our universe to be fundamentally connected? That stage is the fabric of spacetime, a concept that sounds like science fiction but is our fundamental reality. Think of a trampoline stretched perfectly flat. Now place a heavy bowling ball in its center. The fabric sinks, creating a deep, curved well around the weight. This simple image is the heart of Einstein's theory of general relativity. Mass and energy do not simply sit within space, they actively mold it. They tell the fabric of the universe how to curve. And this curvature is what we feel as gravity. A rolling marble on that trampoline would spiral inevitably toward the bowling ball, not because of a mysterious force pulling it, but because it is simply following the curved path laid out for it. This is how planets orbit stars and how galaxies hold their shape. They are all traveling along the invisible contours of warped spacetime. Einstein's field equations, the complex mathematics behind this idea, are the precise instructions for how energy and momentum sculpt the cosmos. Without this malleable fabric, the universe would be a static, rigid stage. There could be no dips, no curves, and certainly no shortcuts. This profound warping of reality is the first and most crucial step in visualizing how black holes, the ultimate expression of this curvature, could possibly be connected. Now, let's meet the architects of these cosmic bridges, the entities that twist spacetime into knots, the black holes themselves. This is where the elegant curvature of spacetime becomes a cosmic dead end. We call this point a singularity. It is the final destination at the heart of a black hole, a place where matter is crushed into a volume of zero size. Infinite density. This is not just an unimaginably dense star. It is a boundary where the very concepts of space and time stop functioning. Our understanding of physics simply shatters. The formation of a singularity is gravity's ultimate triumph. Picture a massive star, many times larger than our Sun, exhausting its nuclear fuel. With the outward pressure of fusion gone, nothing can resist the star's own immense gravitational pull. In a cataclysmic instant, it collapses inward, crushing itself out of existence. The entire star, with all its mass, is compressed into an infinitely small point. Theoretical physicist Roger Penrose mathematically proved that, according to Einstein's general relativity, this terrifying outcome is unavoidable. So what truly happens in that central void? Is the singularity a physical wall, a final full stop in the story of matter? Or could it be something else entirely, a tear in the fabric of reality that might serve as a gateway? The very existence of the singularity is a glaring sign that our current laws of physics are incomplete. They work perfectly everywhere else, but they fail utterly here. This failure is what drives the quest for a theory of quantum gravity, a new set of rules that could explain the behavior of the universe at this smallest possible scale. To even dream of invisible bridges linking black holes, we must first confront the nature of their mysterious anchors. The mathematical path that first pointed toward these bridges emerged from a surprising and collaborative source. The mathematics of general relativity, while pointing toward singularities, also contain the blueprint for an escape. In 1935, Albert Einstein and his colleague Rosen were exploring the implications of his own field equations. They were not looking for cosmic shortcuts, they were simply following the math where it led. The path took them to a startling possibility, a bridge. This theoretical structure, now famous as a wormhole, was formerly called an Einstein-Rosen bridge. It proposed a tunnel through the very fabric of spacetime, connecting two distant regions with a shortcut. Picture the universe as a vast sheet of paper. The normal route from one point to another is a long line across its surface. But if you fold that paper, bringing those 2 points together, the Einstein-Rosen bridge is like poking a hole directly through the fold. The journey that was once an immense distance becomes a single step through a tunnel. This was not science fiction. It was a legitimate, if highly speculative, solution to the most robust theory of gravity we possess. The original conception of this bridge was deeply tied to the nature of a black hole. Einstein and Rosen saw it as a possible structure linking a black hole to its theoretical opposite, a white hole. A white hole would be a region of spacetime where nothing could ever enter, only expel matter and energy outward. It would be a cosmic gusher, the reverse of a black hole's endless drain. For a fleeting moment, this bridge seemed to offer a way through the terrifying singularity, a passage to another part of the cosmos or even another universe entirely. But the hope was short-lived. Calculations quickly revealed a fatal flaw. These primitive wormholes were fantastically unstable. The moment even a single particle of matter or a flicker of light tried to pass through the tunnel, it would snap shut. The bridge would collapse into a pinprick faster than the speed of light, crushing anything inside. It was like a tunnel made of soap film, disappearing the instant you try to touch it. For decades, this seemed to be the final word. Wormholes were a beautiful mathematical ghost, a cosmic possibility that reality itself forbade. Yet, the seed of an idea was planted. The bridge existed in theory. The question was no longer if such a structure could be, but what would it take to hold the door open? The answer would require a substance that defies the very nature of gravity itself. To keep that cosmic tunnel from snapping shut in an instant, you would need to line it with a substance that defies reality as we know it. We call this theoretical material exotic matter. It does not behave like the atoms and molecules that make up our world. Normal matter, the stuff of stars and planets and us, always exerts a positive gravitational pull. It warps spacetime inward, creating the attractive force we call gravity. Exotic matter would do the exact opposite. It would warp spacetime outward, generating a kind of negative gravity, a repulsive pressure. Think of it as cosmic anti-gravity, a force that pushes the walls of the wormhole apart, propping the throat open against its own immense desire to collapse. This is not mere speculation, but a requirement born from the mathematics of general relativity. Without this negative energy density threading the tunnel, the bridge is doomed. It becomes a cosmic trapdoor that slams closed faster than light can travel. So where could such a bizarre substance possibly exist? The answer lies in the strange, probabilistic realm of quantum physics. Under certain conditions, the vacuum of empty space itself can exhibit negative energy density. A famous demonstration is the Casimir effect. When you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they are pushed toward each other by a mysterious force. This happens because the quantum fluctuations in the space between the plates are more restricted than those outside, creating a subtle pressure difference. The region between the plates effectively has less energy than the surrounding vacuum, a tiny pocket of negative energy. This is not bulk exotic matter you could hold in your hand, but it is a real, measurable phenomenon that proves the underlying principle is not pure fantasy. Physicists like Kip Thorne have rigorously explored what it would take to build a traversable wormhole, a stable bridge you could actually pass through. Their conclusion was unanimous. A lining of exotic matter is not just helpful, it is absolutely essential. It would have to form a perfect ring or shell around the wormhole's throat, a continuous thread of repulsive gravity creating a permanent doorway. The staggering challenge, of course, is that we have no idea how to create or harvest this material in the vast quantities required. Our entire observable universe seems to be made of normal, positively gravitating matter. The search for exotic matter, or a deeper understanding of how to generate its effects, is one of the great frontiers of theoretical physics. It is the key that could transform a beautiful mathematical ghost into a tangible structure in the cosmos. And this leads us directly to a specific, and perhaps the most promising, candidate for such a bridge in nature. The crushing finality of a point singularity is not the only possibility. Some black holes spin, and this rotation changes everything. Described by the brilliant mathematics of physicist Roy Kerr, these rotating black holes do not contain a point of infinite density. Instead, they hold a ring singularity, a loop of unimaginable energy shaped like a cosmic donut. This is not a solid ring you could touch, but a boundary where physics as we know it ceases to exist. The rotation is so powerful it flattens the collapse into this unique form, creating a structure that is far more than a dead end. The spin of a Kerr black hole also warps the fabric of spacetime around it in an extreme way, an effect known as frame dragging. Imagine stirring a cup of tea with a spoon. The honey at the center gets caught in the vortex, dragged around by the spoon's motion. Now, replace the honey with the fabric of reality itself, and the spoon with a black hole spinning at nearly the speed of light. The entire region of space around the black hole, called the ergosphere, is forced to rotate with it. Nothing can stand still. It is a cosmic whirlpool from which not even space can escape. This incredible geometry opens up a stunning possibility. The ring singularity at the center may not be a wall, but a portal. The mathematical solutions suggest that if you could somehow navigate the chaotic inner horizons and approach this ring, you might not be torn apart by infinite gravity. You could, in theory, pass through the ring itself. What lies on the other side? The equations point to a mirror universe, or perhaps a distant region of our own cosmos, a reality on the far side of the gravitational maelstrom. This is not just a gateway through space, but potentially through time as well. The twisted spacetime near the ring could allow for closed time-like curves, pathways that loop back on themselves. An object following such a path could, in theory, travel into its own past. This makes the Kerr black hole the most promising candidate for a natural wormhole, a bridge built by the universe itself. Its ring singularity is the door, and its rotating frame is the hall. But a single bridge is just the beginning. What if these cosmic doorways are not isolated but part of a vast, interconnected web? Could the universe be threaded with invisible wires, connecting its most massive objects like beads on a string? Beyond the tunnel-like structure of a wormhole, another form of bridge might exist, one built from the very cracks in reality's foundation. These are cosmic strings. They are not made of any ordinary material, but are thought to be one-dimensional flaws in spacetime itself, frozen relics from the universe's first chaotic moments after the Big Bang. A cosmic string would be thinner than a single atom, yet a single inch of it could weigh more than a mountain range. Imagine a crack in a sheet of ice, a flaw in the crystal structure that runs through it. Now, picture that crack not in ice, but in the fabric of the cosmos under unimaginable tension. This is the essence of a cosmic string. Now, place two black holes in the cosmos. If a cosmic string were to stretch between them, its ends could be anchored firmly by their immense gravity. The string would become a superhighway, a permanent, ultra-strong cable tethering these cosmic giants across billions of light years. The sheer energy density of the string would warp the spacetime around it so dramatically that it could create a shortcut, a trough in the cosmic landscape that makes the journey between the 2 points far shorter than traveling through normal space. While we have not yet found direct proof that cosmic strings exist, their theoretical properties make them perfect candidates for the universe's fundamental infrastructure. They could weave an immense, invisible web, a cosmic network linking the most powerful objects in existence. This vision of connectivity forces us to see the cosmos not as a collection of isolated islands, but as a single, intricately woven tapestry. This radical idea suggests that our three-dimensional reality might be a holographic projection from a two-dimensional surface. The holographic principle emerged from a puzzle about black holes, and where information goes when it vanishes behind the event horizon. If the information is truly lost, it violates a core rule of quantum mechanics. The solution, proposed by physicists like Leonard Susskind, is that the information is not lost at all. Instead, it is perfectly encoded like a hologram on the surface of the black hole's event horizon. Every star, planet, or atom that falls in leaves a tiny imprint on this spherical surface, its data scrambled across the boundary like pixels on a cosmic screen. The entire three-dimensional interior of the black hole is described by the information painted on its two-dimensional shell. This is not just a fact about black holes. It could be a fundamental property of the universe itself. Our own reality, with its rich depth and volume, might be a holographic projection from the distant boundary of the cosmos. This points toward a profound and inescapable interconnectedness. Everything is linked to everything else through this underlying code. Now, take this idea of connection to its ultimate conclusion. What if two black holes are quantum entangled? This is the heart of the ER equals EPR conjecture. ER stands for the Einstein-Rosen bridge, the wormhole. EPR stands for Einstein, Podolsky, and Rosen, who first identified the spooky phenomenon of quantum entanglement. The conjecture boldly proposes that these two ideas, wormholes and entanglement, are two different descriptions of the same thing. If two black holes are entangled, then a wormhole, a bridge in spacetime, automatically connects them. Their connection is not just a spatial shortcut. It is a physical manifestation of their quantum link. Entanglement, that strange bond where particles instantly influence each other across any distance, might be literally woven into the fabric of spacetime as these invisible tunnels. This transforms our view of the cosmos. The universe is not just filled with isolated objects. It could be a vast, cosmic network, a web of entanglement with black holes acting as the nodal points. The largest structures we see, the great cosmic filaments of galaxies stretching across the void, might be shadows of this deeper, quantum gravitational architecture. The line between the incredibly small world of quantum particles and the immense realm of gravity completely blurs. These invisible bridges are not anomalies, they are fundamental features, stitched into the operating code of reality itself. At the heart of our own Milky Way, a silent giant resides. Sagittarius, a star, is a supermassive black hole, weighing in at over 4 million times the mass of our Sun. It is not a lonely predator, but the gravitational anchor for our entire galaxy. Its immense pull dictates the orbits of billions of stars, orchestrating a cosmic dance on a scale we can barely comprehend. This is not unique to our home. Nearly every large galaxy we observe has such a behemoth at its core, a gravitational monarch ruling from the center. Their presence raises a profound question. Could these supermassive black holes be more than just isolated rulers? Could they be connected to one another across the vast emptiness of intergalactic space? The large-scale structure of the universe offers a clue. Galaxies are not randomly scattered. They are arranged in a colossal web, with great filaments of galaxy clusters stretching across billions of light years, separated by immense voids. Some theoretical models propose that this visible cosmic web is mirrored by an invisible one, a network of wormholes or spacetime bridges linking the central supermassive black holes of these galaxies. It would be a cosmic subway system, with each black hole acting as a station. The energy required to power such an unimaginable network is almost beyond calculation. Yet, we may already be observing the engines that could sustain it. Look at quasars, the most luminous objects in the universe. These are distant galaxies with supermassive black holes at their centers that are actively feasting on matter. As vast clouds of gas and stars spiral inward, they heat up to incredible temperatures, releasing blinding energy that outshines the entire galaxy. An active galactic nucleus is a similar phenomenon, a supermassive black hole in a state of violent consumption. The energy output is staggering, enough to power jets of matter that shoot out across space for millions of light years. Could some of this titanic energy be channeled not just outward, but inward, stabilizing a bridge to another point in the cosmos? Intriguingly, astronomers have sometimes detected strange correlations between quasars separated by vast distances. They appear to flicker or flare in ways that suggest a connection, as if an invisible thread tugs on both ends simultaneously. While other explanations exist, the possibility remains that we are seeing hints of the universe's deepest infrastructure. These supermassive giants may be far more than cosmic vacuum cleaners. They could be the key nodes, the bustling interchanges, in a hidden transportation network woven into the fabric of reality itself. Such a journey would demand power sources that dwarf our entire civilization's output. To even approach a bridge linking black holes, we must first learn to harvest energy on a cosmic scale. One of the most promising methods lies in the ergosphere of a spinning black hole, a region where space itself is dragged at near light speed. Here, a theoretical maneuver known as the Penrose process could unlock immense power. Imagine an object enters this whirling region of distorted space and splits into two pieces. One fragment falls into the event horizon, sacrificed to the black hole's grip, while the other is flung outward. Due to the bizarre physics of frame dragging, the escaping fragment can carry away more energy than the original object possessed. It is like stealing rotational energy from the black hole itself. In the context of a stable wormhole, this extracted power could be the very thing needed to reinforce the tunnel's throat, providing a steady stream of energy to counteract the relentless pull of gravity. Another, more subtle energy source is Hawking radiation. This is a quantum phenomenon where a black hole slowly radiates particles, losing mass over astronomical timeframes. For a supermassive black hole, this glow is trillions of times weaker than the cosmic microwave background, utterly undetectable. Yet, the principle is profound. It demonstrates that black holes are not entirely black. They have a temperature. A far future civilization might devise a way to collect and manipulate this radiation, perhaps using it as a control mechanism or a power source for delicate instruments near the bridge's entrance. The energies involved are almost beyond human comprehension, but the theoretical pathways exist. They are the blueprints for a technology that could one day turn these cosmic bridges from mathematical wonders into usable roads. But powering the journey is only half the challenge. What would happen if we tried to send a simple message, a single pulse of light, through the tunnel? A journey through a cosmic bridge is not just a trip across space, but a voyage through time itself. The very act of traversing a wormhole forces us to confront the nature of causality, the simple and comforting idea that cause must always come before effect. This foundational rule of our universe is thrown into chaos by the physics of these tunnels. If one end of a wormhole is moved at a significant fraction of light speed, or placed near an incredibly strong gravitational field like a neutron star, Einstein's time dilation would take effect. Time would pass at different rates for the two mouths of the bridge. One end could age years while the other ages only days. This would desynchronize them, creating a situation where the exit point exists at an earlier time than the entrance. Stepping through such a bridge would not merely transport you to another location, you would be traveling into your own past. This creates what physicists call a closed time-like curve, a path through spacetime that loops back on itself. The most famous nightmare of this scenario is the grandfather paradox. What if you traveled back and accidentally prevented your own grandfather from meeting your grandmother? You would never be born, so you could never have traveled back to create the problem in the first place. It is a logical loop that seems to shred the fabric of reality. How could the universe possibly allow such a contradiction? Physics offers potential escape routes. One compelling idea is the Novikov self-consistency principle. This principle asserts that the past is immutable. Any actions you take while in the past were always a part of history. You simply could not create a paradox. If you travel back, you were always there. Your attempts to change events would inevitably fail through a bizarre confluence of coincidences, a series of unlikely accidents that guarantee history unfolds exactly as it always did. You might try to prevent a meeting, only to inadvertently cause it. The universe, in this view, is a single, self-consistent story, and time travelers are merely playing out a role that was written for them from the beginning. Another, more dramatic resolution comes from the quantum world. The moment any action is taken that would create a genuine paradox, the wormhole itself might be destroyed. The immense gravitational feedback from the logical inconsistency could cause the tunnel to collapse instantly, severing the connection and protecting the timeline. The bridge acts as its own cosmic circuit breaker. This is not just a theoretical game. The preservation of causality is a fundamental puzzle that any practical traversable bridge must solve. It pushes our understanding of physics to the absolute brink, forcing us to question whether time is a river we can only float down, or an ocean we can learn to navigate. Our reality may be far richer than the three dimensions we perceive. String theory, one of the most ambitious frameworks in physics, suggests that the fundamental building blocks of the universe are not tiny dots of matter, but unimaginably small, vibrating loops of energy. Think of a guitar string. Pluck it one way and it produces a specific note, which we could interpret as an electron. Pluck it another way and the vibration creates a different note, a photon. In this view, every particle in existence is just a different resonant frequency played on these cosmic strings. But for the mathematics of this beautiful symphony to work, the strings cannot vibrate in just the three dimensions of length, width, and height. They require more room, a total of 10 or even 11 dimensions to produce the full spectrum of particles and forces we observe. Where are these extra dimensions? The theory suggests they are compactified or curled up at every single point in space, too tiny for us to ever detect directly. It is as if every location in our universe contains a hidden, microscopic origami of additional spatial directions. This multidimensional landscape completely reframes our understanding of black holes and their bridges. A wormhole might not be a tunnel that simply bends through our familiar three-dimensional space. Instead, it could be a shortcut that passes through one of these compactified higher dimensions, a route that is completely invisible and inaccessible from our limited viewpoint. The journey that looks impossibly long from our three-dimensional perspective could be a quick hop through this hidden geometric fold. This idea is deeply connected to the concept of brains, which are shorthand for membranes. In string theory, our entire universe could be a three-dimensional brain, a kind of cosmic slice floating within a higher dimensional space called the bulk. Other brains, hosting other universes with entirely different laws of physics, could be floating right alongside our own, separated by a minuscule gap in a higher dimension we cannot perceive. A black hole could be a place where our brain is pinched so tightly that it touches another brain, creating a bridge. Even more profound is the suggestion that the collision of two such brains could have been the event we call the Big Bang, the violent birth of our cosmic reality from a higher dimensional architecture. From this perspective, the invisible bridges linking black holes are not just curiosities within our universe. They could be threads woven through the higher dimensional bulk, connecting not just distant locations, but potentially different brains, different universes entirely. This multidimensional vision offers a breathtaking new landscape for understanding cosmic connectivity. It transforms black holes from simple gravitational pits into potential portals within a far vaster, hidden cosmos. But how could we ever hope to find evidence for something so abstract, so far beyond our direct sensory experience? The bridge itself could carry a message, written not in words but in gravity. If two black holes are connected by a wormhole, their vibrations are intrinsically linked. When one black hole merges with another or swallows a star, it rings like a bell, sending gravitational waves rippling through the cosmos. In a pair of bridged black holes, these waves would not travel solely through the outside universe. A portion of the vibration would shoot directly through the tunnel, arriving at the partner black hole slightly before the waves that took the long way around. This would cause the second black hole to ring in a specific, synchronized echo. Our gravitational wave observatories, like LIGO and VIRGO, might one day detect this strange chorus, a faint, premature tremor in the signal that hints at a hidden shortcut stitching the two giants together. The light passing through a bridge could also carry information. Imagine a wormhole perfectly aligned between a distant quasar and our telescopes. We would see the brilliant quasar directly, but we might also see a second, fainter image of it, a ghostly twin created by light that traveled through the throat of the bridge from a completely different angle. This phantom image would have the exact same spectral fingerprint as the original, a perfect cosmic duplicate with no visible source of its own. The very stability of a traversable bridge might also broadcast its existence. The exotic matter holding it open would create a bizarre region of repulsive gravity around its entrance. A star passing near this region would not be pulled inward, but instead might be gently pushed away, its path deviating in a way that defies the pull of any normal black hole. These are the subtle fingerprints we are learning to search for, the faint whispers in the data that could signal a doorway in the cosmos. Finding one would not just confirm a theoretical idea, it would fundamentally alter our place in the universe, revealing that the vast emptiness of space is an illusion and that we are living within a deeply connected cosmic web. The same spooky connection that baffled Einstein could be the very glue holding spacetime together. At the tiniest scales of reality, two particles can become quantum entangled, their fates intertwined in a way that defies distance. Measure the spin of one particle here on Earth, and its partner, even if it's on the other side of a galaxy, instantly assumes a corresponding state. This is what Einstein famously called spooky action at a distance, a phenomenon that seemed to violate the cosmic speed limit of light. For decades, it was a ghost in the machine of quantum theory. Then, a revolutionary idea emerged, known as the ER=EPR conjecture. It proposes a breathtaking solution that this spooky quantum link is not some invisible signal, but a physical bridge in the fabric of spacetime. An Einstein-Rosen bridge, a microscopic wormhole, geometrically connects the two entangled particles. The connection is not magical, it is architectural, a tiny tunnel woven into the universe's foundation. This single conjecture stitches together the two great pillars of modern physics, quantum mechanics and general relativity. It suggests that if you could create two black holes in a perfectly entangled state, a wormhole would not just be possible, it would be mandatory, a natural consequence of their quantum relationship. The universe, in this view, is not built with space and then filled with quantum particles. Instead, spacetime itself may be a tapestry emerging from a vast, underlying network of quantum entanglement. Every entangled pair is a stitch in that cosmic fabric. So how could we possibly scale this microscopic phenomenon into a bridge we could traverse? The challenge is monumental. Entanglement is incredibly fragile, easily shattered by any interaction with the outside environment. To build a stable, macroscopic wormhole, you would need to create and protect an immense amount of quantum entanglement, perhaps on the scale of an entire star's worth of particles, all linked together in perfect synchrony without decoherence. It would be like trying to build a cathedral out of soap bubbles, each one perfectly aligned and never popping. Yet, the principle points a way forward. The invisible bridges linking black holes across the cosmos may not be rare anomalies. They could be the most natural thing in the world, simply the large-scale expression of the quantum threads from which all of reality is woven. The grandest structure known to exist is the cosmic web. Look at a map of the universe on its largest scales, and you will not see a random scattering of lights. Instead, you find a breathtaking architecture, an intricate lattice of brilliant galaxy filaments surrounding incomprehensibly vast dark voids. This is not a static sculpture. It is a dynamic, evolving network, and its primary architect is an entity we cannot see, dark matter. This mysterious substance, which makes up about 27% of the cosmos, does not emit, absorb, or reflect light. Its presence is known only through its immense gravitational pull, a ghostly hand that sculpts the visible universe from the shadows. The galaxies we see are merely the glittering ornaments draped over this invisible framework. Now, consider the possibility that this dark matter scaffold does more than just shape where galaxies form. Could it also provide the foundation for the invisible bridges linking black holes? Some speculative theories propose exactly that. The vast halos of dark matter that envelop every galaxy might act as natural stabilizers for wormholes. The unique gravitational environment within these halos could be what pins the mouth of a bridge in place, preventing it from drifting or collapsing. In this view, the cosmic web is not just a structure of galaxies, but a network of potential gateways, with the dark matter filaments themselves serving as the hidden highways connecting them. An even more profound possibility emerges from the idea that dark matter itself could be made of primordial black holes. These would not be the black holes formed from dying stars, but ones created in the searing density of the universe's first second, a cosmic fossil from the dawn of time. If this is true, then the dark matter halo around a galaxy is not a smooth cloud of unknown particles, but a swarm of countless tiny black holes. The network of bridges would then be direct and fundamental, with these primordial black holes acting as the nodal points of the web, intrinsically connected to one another through spacetime tunnels. The distribution of dark matter, which we can map through its gravitational lensing of distant starlight, might not just show us where the mass is. It could be a literal blueprint, revealing the most probable locations for these cosmic shortcuts. This shifts our entire perspective. Searching for a wormhole would no longer be a random quest. We would focus our attention on the densest knots of dark matter, the intersections of the great cosmic filaments, where the gravitational landscape is most complex. These junctions could be the universe's natural transit hubs. This vast, invisible architecture forces us to ask a deeper question. What is the ultimate function of such an immense, interconnected system? Such a profound network forces us to confront a deeply puzzling possibility. Are these cosmic bridges natural features of the universe, or could they be the ultimate artifacts, constructed by a civilization of unimaginable power? The universe itself seems capable of forging rudimentary versions. In the frenetic energy of the Big Bang, when the fabric of spacetime was still fluid and fluctuating, tiny wormholes could have been woven into existence like bubbles in a boiling pot. They might also form as a natural consequence of a black hole's violent birth, a cosmic knot tied in the fabric of reality during the collapse. Yet, these natural bridges would almost certainly be microscopic, fleeting, and violently unstable, snapping shut in an instant. A tunnel you could actually travel through is a different matter entirely. The mathematics is clear. A stable, traversable bridge would not last without constant, intelligent support. It would need a perfect lining of exotic matter, a structure precisely engineered to withstand the relentless pull of gravity. This suggests a creator, a builder. Imagine a civilization so advanced it has transcended planetary concerns, a Type 3 civilization on the Kardashev scale. Such a society would command the entire energy output of its galaxy. For them, building a network of bridges between stars would be a logical next step, the ultimate infrastructure project. They would not build with steel and concrete, but with spacetime itself, using technologies that would seem like pure magic to us. They might stabilize a wormhole by threading it with controlled quantum fields, or by manipulating the fabric of higher dimensions we cannot even perceive. This transforms the search for these structures into something far more profound. Finding a stable, traversable wormhole would not just be a discovery in physics. It could be our first encounter with the archaeological remains of a hyper-advanced intelligence. The very existence of such a bridge might be the signature we have been searching for in our quest to find other life in the cosmos. But with such an immense discovery comes an equally immense caution. If these bridges are out there, who or what might be using them? The technology that opens a doorway also invites something through from the other side. The dream of stepping through a cosmic doorway comes with terrifying realities. The journey through a bridge linking black holes would be the most perilous voyage any traveler could ever attempt. Long before you even reach the mysterious throat of the wormhole, the difference in gravitational pull would become your first and most brutal enemy. Your feet, closer to the immense gravity, would be pulled with vastly more force than your head. You would not simply feel heavier, you would be physically stretched, pulled into a long, thin stream of atoms. This is spaghettification, a gruesome but accurate term for being torn apart by extreme tidal forces. No known material could withstand this. Even a starship forged from the strongest theoretical alloys would be shredded into a line of elementary particles. But suppose a civilization found a way to counteract this, perhaps by generating a perfect, uniform gravitational field inside their vessel. The dangers have only just begun. The tunnel itself, even if held open by exotic matter, might be filled with a maelstrom of high-energy radiation, the leftover scream of quantum particles created and annihilated in the violent spacetime of the bridge. It could be like trying to swim through the heart of a star. The very fabric of the tunnel might also be chaotic, rippling with unpredictable quantum fluctuations that could shake a ship apart or randomly alter its fundamental properties. The exit presents another layer of uncertainty. You might successfully navigate the tunnel, only to emerge into a deadly environment. The other end could be orbiting a hostile, radiation-blasting star, or deep within the turbulent core of a distant galaxy. Worse, it could open into a completely different era. You might step out 1,000,000 years into our own past, or 1 billion years into the future, with no way to return to your own time. And then there is the ultimate terror, the collapse of the bridge itself. Despite all stabilization, the tunnel is a dynamic structure. A fluctuation in the exotic matter lining, a shift in the gravitational fields of the anchoring black holes, or even the act of your passage could trigger a catastrophic failure. The throat of the wormhole would pinch shut, severing the connection. Anything inside would be lost forever, not to a black hole, but to a sealed-off pocket of spacetime, its final fate a complete and eternal mystery. Any mission through such a bridge would demand technologies we can barely dream of. Shields that can manipulate gravity itself and propulsion that borders on magic. It would be a monumental gamble, a roll of the dice against the most fundamental laws of physics. Yet, if such a journey is possible, even in theory, could the existence of these bridges help solve some of the cosmos's most enduring mysteries? The greatest puzzle in modern cosmology is not what holds the universe together, but what is tearing it apart. We call this mysterious force dark energy, a repulsive pressure causing the expansion of the cosmos to accelerate. Its nature is completely unknown, but one radical theory points to a familiar culprit: the invisible bridges themselves. Imagine the vacuum of space not as true emptiness, but as a seething, bubbling foam. At the tiniest possible scale, the Planck length, virtual particles and energy fluctuations constantly pop in and out of existence. This quantum foam, according to some physicists, could be threaded with an unimaginably dense network of transient, microscopic wormholes. These are not tunnels for travel, but fleeting knots and loops in the fabric of spacetime itself. The collective effect of this foamy structure could be a pervasive negative pressure, a kind of background hum of repulsive gravity woven into the cosmos. On the grandest scales, this negative pressure would act like a constant push against the pull of normal matter and dark matter, forcing galaxies to fly away from each other at an ever-increasing rate. In this breathtaking vision, the same fundamental phenomenon, the spacetime bridge, operates at two vastly different scales. The microscopic quantum foam of wormholes drives the accelerated expansion of the entire universe, while the macroscopic, stabilized versions could link supermassive black holes. It is a profound symmetry, a single architectural principle governing both the cosmic web's largest structures and its ultimate fate. This remains a highly speculative idea, far from the scientific mainstream. Yet, it powerfully illustrates a deeper truth. Unraveling the mystery of black hole bridges is not an isolated quest. It is intrinsically linked to the greatest questions we can ask about the cosmos. The fate of every galaxy, the final destiny of the universe itself, could be written in the language of these invisible tunnels. These cosmic bridges are not eternal monuments. They are living entities with their own stories of birth, life, and death. The opening chapter could be written in the first chaotic moments after the Big Bang, when the fabric of spacetime was a seething, turbulent foam. Here, quantum fluctuations could have spontaneously stitched together microscopic tunnels, tiny wormholes flickering in and out of existence like bubbles in a boiling pot. Another potential birthplace is far more deliberate, the deep quantum entanglement of two black holes. If the ER equals EPR conjecture is correct, then when two black holes become intricately linked on a quantum level, a bridge between them must form as a natural geometric consequence. The universe itself forges the connection, but this newborn bridge is incredibly fragile, a delicate thread in the cosmic tapestry. Its youth is a period of extreme peril, where the slightest disturbance, the passage of a single photon, could cause it to pinch shut in an instant. It is a doorway that slams closed the moment anyone tries to turn the knob. For the bridge to survive this volatile infancy, something must intervene to hold it open. This is where the exotic matter lining comes in, acting as a permanent brace, a reinforcement that allows the tunnel to transition into a stable, mature state. A successfully stabilized bridge enters its long adulthood, a phase that could span billions of years. It becomes a permanent fixture, a cosmic landmark silently connecting two distant points in space and time. Think of it as a geological feature, but woven from spacetime itself, as enduring as a mountain range and far more mysterious. For eons, it simply exists, a hidden tunnel in the architecture of the cosmos, potentially used by natural processes or even by intelligences we cannot fathom. Yet, nothing in the universe lasts forever. The death of a wormhole bridge could come in several ways. The most gradual end would be through the slow evaporation of its black hole anchors. If Hawking radiation causes the black holes at either end to slowly lose mass and eventually vanish in a final pulse of energy, the bridge would lose its foundations. The doorway would dissolve, its frame crumbling away. A more violent demise could come from a catastrophic encounter. If another massive object, like a star or a second black hole, collided with one of the mouths, the immense gravitational shockwave could rupture the delicate structure of the tunnel, tearing the fabric of the bridge apart. Or the exotic matter lining that has sustained it for so long could itself decay or become unstable. That perfect ring of negative energy could develop a fault, a weak point where gravity finally wins. The collapse would be swift and total. The throat of the wormhole would constrict, severing the connection. Any matter or energy still inside would be trapped forever, crushed or ejected as the bridge violently dissolves. This final death rattle might release a unique burst of energy, a last scream of gravitational waves or a flash of high-energy radiation, a signature that one day our detectors might recognize. Understanding this entire life cycle, from quantum birth to violent death, transforms our search. We are not just looking for a static object, we are hunting for a structure at a specific point in its cosmic existence. It tells us to look not only in the densest parts of the cosmic web, but also to consider the age of the universe around us. The early universe might have been rich with infant bridges, most of which collapsed instantly. Today, we are more likely to find the rare, mature specimens that have been stabilized and have endured. This temporal perspective connects our quest to the deep past and the far future of the cosmos, framing the search for these invisible bridges as a form of cosmic archaeology. The original vision for a cosmic bridge was not a tunnel between two black holes, but a passage from one reality to another. Einstein and Rosen's first model connected a black hole to its perfect opposite, a white hole. If a black hole is a cosmic drain from which nothing can escape, a white hole is its irreversible twin, a cosmic fountain. It is a region of spacetime where matter and energy can only pour outward, a one-way exit gate from which nothing can ever enter. The mathematics of general relativity allows for such an object, a place where gravity has reversed its role entirely, becoming a force of pure expulsion. A bridge terminating in a white hole would offer a truly spectacular exit. Imagine traveling through the dark, silent tunnel only to be violently ejected in a torrent of energy, erupting into a new region of spacetime in a blinding flash. This theoretical fireworks display could explain some of the most energetic and brief events we see in the cosmos. Perhaps the mysterious fast radio bursts, those intense millisecond flashes of radio waves from deep space, are the distant echoes of such a white hole event. Or maybe some types of short gamma-ray bursts, the most powerful explosions since the Big Bang, are not the collisions of neutron stars but the final, spectacular death cry of a white hole at the far end of a collapsing bridge. Yet, the other side of the bridge might be something entirely different. It could simply connect to another black hole in a far-off galaxy, a hidden backdoor linking two cosmic giants. Or, in a more mind-bending possibility, the tunnel might not remain within our universe at all. The equations allow for the bridge to exit into a completely separate cosmos, a parallel reality within the infinite multiverse. The destination remains one of the most thrilling unknowns, a question mark at the end of a theoretical road. But what if we did not have to wait for the universe to provide a bridge? What if we could learn to build one ourselves? Building a bridge across the cosmos would be the ultimate engineering feat, dwarfing every project in human history. The first step alone is staggering. You would need to create or acquire two black holes. This is not about finding them in space, many exist, but about moving them or forging new ones, a task requiring control over stellar life cycles and gravitational forces we can barely comprehend. Once you have your two anchors, the real work begins. The tunnel between them must be threaded with a perfect, unbroken lining of exotic matter, the substance with negative gravity. We are not talking about a few grams, but a quantity sufficient to encase a cosmic throat, a ring of repulsion holding back the crushing weight of two singularities. Generating this could mean manipulating the quantum vacuum of empty space on a planetary scale, or harnessing the raw power of stars to twist the fabric of reality into a new, stable shape. The geometry of the tunnel itself would need to be flawlessly calibrated. A single irregularity in the curvature could turn the passage into a deadly funhouse mirror, stretching a ship into a stream of atoms or spitting it out into a random point in time. The energy budget for such a project is almost a philosophical concept, demanding the total output of a star like our Sun for centuries, perhaps even millennia. And all of this is before confronting the most baffling problem of all, the potential for time travel and the paradoxes it creates. To make a wormhole a reliable tool, you would need to master causality itself, ensuring that stepping through the door does not unravel the timeline you left behind. This endeavor represents the absolute pinnacle of what is possible when theoretical physics meets engineering on a cosmic scale. It is a testament to the audacity of intelligence. Yet, this monumental task forces a humbling question. Why would we ever need to build one, when the universe itself may have already woven an entire network of bridges, waiting in the darkness to be found? The profound silence of the cosmos is one of its greatest mysteries. We call this the Fermi paradox. Given the sheer number of stars and planets, the universe should be teeming with life, a vibrant galactic community. Yet when we listen, we hear nothing but a vast, unnerving quiet. One compelling answer may lie not in the emptiness of space, but in its hidden connectivity. An advanced civilization would not lumber across the interstellar void in slow, generational ships. That would be like trying to cross an ocean on a raft when superhighways exist just beneath the surface, invisible to you. For a species that has mastered the architecture of spacetime, the true network of travel would be the cosmic bridges linking black holes. These wormholes would form a system of instantaneous transit, a subway for the stars. Their vessels would not emit the telltale signatures of rocket exhaust or radio chatter we typically search for. They would simply depart one gateway and appear at another, leaving no trace in the space between. This explains the great silence not as an absence of others, but as a failure of our perception. We are like ants on a forest floor, unaware of the hikers using the trails above the canopy. Our entire planet, our entire stellar neighborhood, might be a quiet backwater, far from the bustling interstellar intersections. The traffic of galaxies could be flowing all around us, using a transportation grid woven into the fabric of reality itself. This transforms the search for extraterrestrial intelligence. We should not only point our telescopes at distant planets, but also at the strange gravitational signatures around black holes, looking for the subtle fingerprints of a maintained and used gateway. The quest to understand these invisible bridges is no longer just a question of physics. It is the first step in a new kind of archaeology, the search for the ruins of an active, universe-spanning civilization. Our new ears of steel and glass are now listening to the universe's faintest tremors. When two black holes spiral together and merge, they shake the fabric of spacetime, sending out gravitational waves that our observatories can detect. But what if those two black holes were not isolated, but connected by one of these invisible bridges? The death of that bridge would sound nothing like a normal merger. Instead of the classic rising chirp as two black holes coalesce, the collapse of a wormhole would be a violent, sudden event. It might produce a sharp, high-frequency pop in the gravitational wave data, a unique sonic signature of a tunnel snapping shut. There is another, more subtle sound to listen for. A stable bridge, when jostled by a passing star or a surge of energy, would ring like a cosmic bell. These quasi-normal modes are specific vibrational patterns, a faint, lingering hum in the wake of the disturbance. As our detectors grow more powerful, from the ground-based LIGO and VIRGO to the future space-based observatory LISA, we are tuning our instruments to hear these whispers. We are no longer just looking at the cosmos. We are listening to its hidden architecture, straining to catch the echo of a collapsing bridge or the resonant ring of a stable one. This incredible observational frontier brings the search from the theoretical heavens right back to our own cosmic neighborhood. A gateway to another galaxy could be hidden in the heart of our own. At the center of the Milky Way, the supermassive black hole Sagittarius A star, with its 4 million solar masses, anchors our entire spiral island of stars. Its immense gravity is the silent conductor of our galactic dance, But it might also be something far more, one end of a cosmic bridge. If such a structure is real, where could this local door lead? The most compelling destination is our closest major neighbor, the Andromeda galaxy. Its own colossal black hole, known as M31, would be the perfect counterpart. These two titans, separated by 2.5 million light-years of void, could be invisibly linked by a single thread of distorted spacetime. Think of the sheer scale, a shortcut stitching together the two largest cities in our local galactic neighborhood. The energy required to hold such a tunnel open across this staggering distance is almost beyond physics as we know it. Yet, if it exists, it would be the ultimate interstellar freeway, a direct route to another galaxy. This is not the only possibility. The other mouth of the bridge might not lead to a familiar place at all. It could open into a distant, unknown region of our universe, far from any mapped galaxy. Or even more profoundly, it could be a doorway to a different time. The exit might emerge in the early, violent universe, or in a far future era long after our sun has died. How could we ever detect such a phantom structure? The answer lies in looking for the subtle ways it would disrupt its surroundings. Astronomers could search for strange, unexplained anomalies in the orbits of stars near Sagittarius A star. A star might follow a path that subtly wobbles or accelerates in a way that cannot be accounted for by the black hole's gravity alone, as if it were being gently nudged by the repulsive force of an exotic matter lining. We might also detect phantom light, unexplained glows or lensing effects with no visible source, perhaps caused by light from the other end of the bridge leaking into our space. The idea transforms our place in the cosmos from a quiet suburb to a potential transit hub. The greatest doorway in the local universe might not be in some distant, exotic quasar, but right here in our own galactic core, waiting in the darkness for us to learn how to see it. This local possibility makes the vast, abstract concept of cosmic bridges intensely, thrillingly personal. This interconnected cosmos challenges our most basic assumptions about reality itself. The universe is not a void punctuated by isolated stars and galaxies. It is a single, deeply woven entity. The existence of invisible bridges forces a profound philosophical shift, moving us from a mindset of separation to one of fundamental unity. The classical idea of locality, the simple truth that objects are only influenced by their immediate surroundings, shatters when a black hole here is physically linked to another one 10 billion light-years away. The separation between here and there becomes fluid, a matter of perspective rather than an absolute fact. This echoes ancient philosophical and spiritual ideas about the oneness of all things, but now this unity is framed not in metaphor, but in the rigorous language of Einstein's field equations and quantum entanglement. If you can step through a doorway and instantly be in another galaxy, what does that truly mean for the concepts of distance and separation? They are not fundamental properties of the universe, but rather emergent features of how we perceive the cosmic landscape. This connectivity also strikes at the heart of our own identity. If a person could travel through such a bridge, are they the same individual upon arrival? Their atoms have been rearranged by the journey. Their personal timeline may be desynchronized from the universe they left, and their very consciousness has experienced a passage that defies conventional physics. The notion of a stable, isolated self begins to blur against this backdrop of cosmic unity. And then there is the haunting question of free will. The possibility of closed time-like curves, those loops in time enabled by wormholes, suggests a universe where the future can influence the past. If you can travel back in time, was your journey always a part of history? Does this mean that every choice you make was predetermined, simply playing out a story that was already written? This does not necessarily eliminate free will, but it redefines it, suggesting that our choices are part of a vast, self-consistent tapestry where our actions in the present were always factors in the past. Confronting these ideas is more than an intellectual exercise. It is an expansion of human consciousness. It reminds us that the reality we experience with our senses is a tiny, limited slice of a cosmos that is far stranger, more complex, and more wonderfully interconnected than we ever dreamed. This journey through the invisible architecture of the universe reveals a single, stunning truth. A black hole's appetite seems to erase reality's very history. This is the information paradox, a conflict that has haunted physics for decades. At its heart is a simple, unbreakable rule of quantum mechanics. Information can never be truly destroyed. You can burn a book, but in theory, if you could collect every single ash particle and trace of smoke, you could reconstruct every word. The information is scrambled, but it still exists. Now, throw that book into a black hole. It crosses the event horizon and is lost forever, seemingly crushed into the singularity. According to Stephen Hawking's original work, the black hole would eventually evaporate through Hawking radiation, leaving behind only a featureless glow of heat. The book, and all the information it contained, would be gone from our universe, a fundamental law broken. But what if the event horizon is not the end of the story? The existence of an invisible bridge offers an elegant escape. The information from the book does not get destroyed at the singularity. Instead, it is carried away, transferred through the wormhole tunnel like a cosmic data cable. It might be imprinted onto the fabric of the bridge itself, or it could be ejected from the other side. That other side could be a different black hole in a distant galaxy, a white hole erupting in a burst of encoded energy, or even a completely separate universe. The information is not lost, it has simply moved, preserving the quantum rulebook and balancing the cosmic ledger. This idea is crystallized in the powerful ER=EPR conjecture. It tells us that the quantum entanglement connecting two particles, which inherently preserves information between them, is the same thing as a physical bridge in spacetime. The spooky connection is the geometry. Therefore, if two black holes are entangled, a wormhole must connect them, and that tunnel automatically acts as a conduit, ensuring information is shared and never lost. Solving the information paradox would be one of the greatest achievements in modern science, finally reconciling gravity with quantum mechanics. These invisible bridges, long the stuff of science fiction, emerge as the universe's ultimate archivists, guaranteeing that no story, no particle, no single bit of data is ever truly forgotten. They weave a cosmos where every event, no matter how small, is eternally recorded in the fabric of reality itself. Our exploration ends not with a full stop, but with an ellipsis, a trail of questions leading into the unknown. We have journeyed from the simple curve of a trampoline to the chaotic foam of spacetime, from the crushing finality of a singularity to the shimmering possibility of a doorway. We have seen how the universe might be stitched together by threads of exotic matter and quantum entanglement, a cosmic tapestry where the largest structures are linked by the smallest phenomena. These invisible bridges are more than just theoretical marvels, they are keys. They could unlock the secrets of dark energy, solve the paradox of lost information, and redefine our very conception of reality from a collection of separate points to a single, interconnected whole. This vision transforms the cold, empty void of space into a living architecture, a network of hidden roads and secret passages. The pursuit of these answers is what drives us to build better telescopes and more sensitive gravitational wave detectors. It is what pushes the human spirit to look at the starry sky and not just see pinpricks of light, but to sense the invisible architecture humming just beneath the surface. The greatest discovery awaiting us may not be a new planet or a new particle, but the realization that we have been living inside a web of cosmic connections all along. We invite you to share your own thoughts on these profound ideas in the comments below. If this journey through the cosmos has sparked your curiosity, subscribe to join us as we continue to explore the deepest mysteries of the universe.